morning to all of you. You can scan.
Good morning, sir.
Yeah, very good morning. So we will wait for a minute to join, others to join. So meanwhile, those who are from Chavasa Engineering College, they can scan this QR code for the attendance. So in the previous class, what we have discussed, so we have finished the Fourier transformation, okay, or we can say DFT, Fourier discrete transformation, and we have discussed some of the properties, okay, basically 10 properties of discrete Fourier transformation, which is important, relevant to your exam concept, okay. Then we have just started the discrete cosine transformation, okay, DCST बोलते हैं, discrete cosine transformation. So why discrete cosine transformation is important, or I can say why Fourier transformation. What is the drawback of Fourier transformation? तो सबसे पहला पॉइंट है आपका जो Fourier transformation कर रहे थे, whenever the image is converted to a frequency domain while using DFT, okay, discrete Fourier transformation, the actual frequency domain representation are in complex format. ठीक है, आपका जो एक्चुअल रिप्रेजेंटेशन था वो आपका कॉम्प्लेक्स फॉर्मेट में था, बिकॉज इफ आई रिप्रेजेंट द इमेज बेसिकली क्या था आपका, इट इज मॉड ऑफ एफ ऑफ यू बी इनटू e to the power of minus j pi uv. Okay, this is a representation. Now जो भी आपका रिप्रेजेंटेशन था, okay, फ्रीक्वेंसी डोमेन में, दिस इज इन द कॉम्प्लेक्स फॉर्मेट. So what is the drawback here? Drawback is now computational in the complex format is much harder. ठीक है, अगर कोई भी प्री प्रोसेसिंग या कंप्यूटेशन करोगे आप तो यहाँ पर थोड़ा डिफिकल्ट था. So that is the reason we have gone for the other transformations. Okay, so one of the other transformation is your discrete cosine transformation. Okay, discrete cosine transformation where where the actual frequency domains are represented in your real format, or we can say real cosine basis function. Okay, real cosine basis function में हम लोग उसको represent करते हैं. Okay, then we have just started the introduction part. So this discrete DST transformation is initially developed in the year 1974 by the two authors called Ahmad and Natarajan and Rao. Okay, so these three authors are combinedly discovered this transformations, okay, DST transformation in the year 1994. So we can say discrete cosine transformation as we are already discussed. So we have differentiate, or we have characterized the different category based on the signal, okay, based on the sinusoidal signal, non-sinusoidal signal, and orthogonal signal. Now this DST, discrete cosine transformation, will be belong to family of sinusoidal unitary transformation. Okay, like DFT. Okay, like DFT, this is also belonging to sinusoidal unitary transformation. Sinusoidal means the basic function. Okay, the basis function or unit function that we are using to reconstruct the frequency images are used sine and cosine values. Fine, that means sinusoidal. जो कि आपका बेसिस फंक्शन है वो आपका साइन या कोसाइन फॉर्म में होगा. Fine. The simple definition: the discrete cosine transformer DSTs consist of set of basis vectors. Again, and what is a basis vector? This is a fundamental signals. I can say fundamental signals or fundamental unit from which we combine this fundamental unit to get an actual image. Okay, or we can say actual frequency images. Okay, now these are the basic vectors. What are the basic vectors? Here the basic vector are sample real cosine function. Okay, sample real cosine function. So we will have, instead of, in case of DFT, what we are having, in case of DFT, we are having imaginary functions. Okay, but here we are having real cosine function. Okay, the main two purpose why we are using the DST is, first of all, it is very useful for image compression. Okay, so whenever you need to compress the image, or reduce the size of the image and transmit is a low bandwidth. So we will always go for the DST, okay, also DCT, okay, discrete cosine transformation, because for image compression purpose it is very helpful. So we can compress the image and transmit the image in lower bandwidth. And second important thing is energy compaction. Okay, the energy compaction in your discrete cosine transformation is much higher compared to the energy compaction in your DFT. So these are the main reason. Okay, these are the main two drawbacks. Okay, the first drawback is, first of all, when we are using the DFT, whatever image you're getting, that is in complex format. So pre-processing is much harder. So that is why we gone for the discrete cosine transformation. Second thing is energy compaction in your DFT, discrete Fourier transformer, is low. Okay, whereas energy compaction in your discrete transformation is high. So up to this point we have discussed in the previous class. Now let us today understand how we can derive a mathematical formula for this one. Okay, and we will compare this DCT with the DFT. Now this is the equation. Okay, this is the equation. Fine, this is the equation which gives the DST for one dimensional. Okay, so this equation, this mathematical equation is nothing but discrete cosine transformation for discrete one dimensional signal. Okay, so what is the formula? Now CU represent your DST. Okay, discrete cosine transformation. Now it is nothing but AU into summation of x equal to 0 to capital N minus 1. Now f of x is your one dimensional discrete signal. Okay, one dimensional discrete signal. And now we can, here we can, now the basic, it is multiplied by the cos of 2x plus u pi by 2n. Now this is in terms of real coefficient of cosine function. Okay, now this is multiplied with real coefficient of cosine function, which is the cos of 2x plus 1 ux by 2n. Now x ranges from 0, 1 to n minus 1. Now this formula is basically denote the, what is denoting? It is a one-dimensional DST, discrete cosine transformation. Similarly, if I want to inverse of it, it will be inverse discrete cosine transform. So basically, we will use the inverse to regenerate the image. Okay, so which is denoted by f of x. Now this will be my original image. Okay, now this is my original image, which is given by summation of u equal to 0 to n minus 1 AU CU. Now C is your frequency domain, or we can say discrete cosine transform coefficient multiplied by cos of 2x plus 1 u pi by 2n. Fine, where u ranges from 0, 1 to n and minus 1. It will be discrete in nature. So the question comes, what is the value of AU here? AU is your constant. Okay, in some books they are written like alpha k. Okay, in some books AU is equal to alpha k likha hoga. Don't be confused. AU is just constant part, and its value will be root over 1 by n if u equal to 0. That means if the u equal to 0, the very first value of u is value will be 1 by root over, and for other values we can write whenever u is not equal to 0, that means u is greater than equal to 1. Okay, so what is the value? It will be value and value will be root over 2n by n. Fine, so this is the representation, mathematical representation for the one-dimensional discrete DCT, discrete cosine transformation, we can say. But what we are not interested in one dimension, because as I already said, the f of the image is represented by f of xy, two dimensional. Yes or no? आपका जो इमेज है हमेशा वो किस में रिप्रेजेंट होता है? वो आपका टू डायमेंशनल डिस्क्रीट सिग्नल में रिप्रेजेंट होता है. So I have to derive, okay, DCT for, okay, so what I am interested, now I have to derive DCT for two dimension. Okay, this will be much similar to this one, but we will now derive for the two dimensions. So let us see how the mathematical equation for that will be look like. Yeah. Now this equation, this is the mathematical equation which is given for two-dimensional. Okay. So what this gives, this is the two-dimensional. Now you can write this is two-dimensional discrete cosine transformation, which is represented by C of UV. Fine. Now I am having two constants here, AU and AB. Now the range of AU will be same. AU will be equal to what? Root over 1 by n if U is equal to 0, and it will be root over 2 by n if V will be equal to, sorry, if U is greater than equal to 1. Okay, similarly, AV will be ranges from, AV will be, A of V will be, it ranges from 1 by root over, sorry, root over 1 by n when V is equal to 0, and it will be 2 by n when V is greater than equal to 1. Now these two are constant. Okay, now sometime I replace this one is alpha k 1 and this one is alpha k 2. Okay, either AU or AB. These are the two frequency domain constant, I can say U. Now, as we said, the image, now this is my actual image which is represented in f of xy. Now I know that the image can be represented in a real coordinate. So x ranges from 0 and y from 0 to n minus 1 and n minus 1. Okay, now I'm having two real coefficient here, cos coefficient, as I already said. So one coefficient is this one. What is this? Cos into 2x plus 1 u pi by 2n. And then next is cos 2y plus 1 u pi v by 2n. Fine. So we are having a two real coefficient in cosine format. Fine. Now this is a mathematical representation for two-dimensional discrete cosine transformation. Similarly, I can apply the inverse. Okay, basically we again apply the inverse to get the original image. If we apply the inverse, the image formula, what we get? We will get the original image, which is f of xy. This is same. Now u and v ranges from 0 to n minus 1. The two coefficient AU and AV, which is same, ranges from 1 by root n for u equal to 0 and root over 2 by n for u is greater than equal to 1. Fine. Now this is my frequency domain image. Then 2 cos, real parameter of cos value, and x, y ranges from 0 to 1. Okay, now this two formula you have to remember. Okay, this two formula we have to remember how to convert an image. Suppose an image is given. Okay, fy, f of xy. Suppose I talk of DCT, discrete cosine transformation. Then it will be represented by P of uv, and its mathematical formula can be derived by this equation. Similarly, if C of uv is given, okay, the frequency domain of is given, so I will apply inverse discrete cosine transformation. Okay, inverse discrete cosine transformation. So what we will get? So we will get the actual image in a spatial domain. Okay, I will get the actual image in spatial domain. Then what is the formula? The formula for this is this one. So I have to apply this formula. Clear? Is it clear to all of you? How we are deriving the DST and IDST? Is it clear? Yes? Is it clear to all of you? So you can note down this formula. Okay, you can note down this formula. All of you can note down this formula.
सर हमें इसका पीडीएफ मतलब पीपीटी और नोट्स मिल सकता है क्या?
एक बार फिर से बोलिए, क्या बोलिए?
सर हम कह रहे हैं कि हमें इसका नोट्स और पीपीटी मिल सकता है.
आप दुमका से बोल रहे हैं?
यस सर.
ओके आई विल, क्योंकि मैं ये नोट्स और पीपीटी जो है ना हम लोग का जो एलएमएस पोर्टल है वहाँ सेट कर रहा हूँ, तो व्हाट आई विल डू, आई विल शेयर दिस पीपीटी ऑन ग्रुप, ओके व्हाट्सएप ग्रुप में मैं शेयर करूँगा, फाइन।
ओके सर। सर इससे पहले जितने क्लासेस हुए हैं उनके भी नोट्स
I will share all the PPTs, okay, all the PPTs
ओके सर,
fine.
ओके सर, थैंक यू सर।
Okay, so then we will move on. Okay. Now this basically represent your basic function of matrix, okay. So जैसे हम लोगों ने पढ़ा था DFT में, अगर DFT में, okay, DFT में, so how to construct a DFT. Now to convert a DFT, what I require the basic function, okay. Then I will multiply the basic function with actual image. Then I will multiply with this one with the basic function of transformation. Okay, so I already discussed this one, how to actually we are getting a DFT. आप basis function use करोगे, basis function to original image, then basis function का transform image. Similarly, अगर आप C discrete cosine transformation निकालेंगे, then I have to take basic cosine function multiply by your original image, okay. Then I will take transformation of basic function, okay, transformation of basic function. Now the question rises here, how to find this basic function, because अगर आप पिछले लैब अटेंड किए होंगे तो लैब में हम बताए थे, तो बेसिक फंक्शन फॉर एवरी डायमेंशन ऑफ मैट्रिक्स इन केस ऑफ DFT, ठीक है. If it is first for 4, so I can use the MATLAB function DFT matrix for 4. So it will generate a basic function for matrix 4. Similarly, 8 will be, लेकिन the basic function is in case of discrete cosine function, which is represented by a Cn, okay, Cn, which is given by root over 2 by n, okay, root over 2 by n. Now these are the values that will be assigned. ठीक है, फिर n equal to, now I can find for, now I can find n equal to 0 के लिए, 1 के लिए, like that, and minus 1 तक करेंगे. Fine, so you can find for the basic function for any of the values, okay. Now we will use this matrix, okay. This is a particular matrix which is used for finding the basic function for the DCT, okay. So generally we does not require this matrix, okay. For calculation purpose, if mathematical calculus, then we require this matrix. Okay, fine. So yeah, so this is an example, okay. This is an example. So we have taken a picture of cameraman, okay. So this is the original image. So if we perform the DST over it, okay, discrete Fourier transformation, the image will be something like this. Now this will be your frequency. Now I can say this is my time domain representation. This will be my time domain representation, and this will be my frequency domain representation. This will be my frequency domain representation. Okay. Now you can see this comparison. Now this in this particular slide, so we have shown the relationship between DFT and DCT. Okay. Now this is my original image. Okay. Now this particular image. Okay, this particular image. So when we will perform the discrete Fourier transformation, and this is image 2, which will be given when you perform the discrete cosine transformation, and this is the image which is provide shifted DFT. So whenever we need a scaling is basically we perform if some of the images will out of boundary value. अगर कुछ part अगर boundary value से बाहर जाएगा, then we have to perform the scaling by the shifting operation. Okay. Now shifting property पढ़े थे हम लोग, how to perform the shifting property. So we will apply the shifting property here. Okay. Now this is a particular shifting property of the DFT. Now you can compare, see the difference here in the both the format. Okay, now this is a DFT because the difference is because this image is basically represented in complex format. Okay, whatever you getting this image, that is in the real part, it's this having a two components. one is you're having a real part, RU, and there is an imaginary part. Okay, and in this particular image, when you converting to DST, okay, discrete Fourier transformation, we are having two real parts only. There is no imaginary part. There are only two real parts, and that to be in cosine function. Okay, that to be in cosine function form. Fine. So you have to remember this one. When we are performing DFT, then the whatever we are getting, there will be having this image. We have two parts. One is a real and imaginary part. But in this case, when you are performing the discrete cosine transformation, the output will be whatever the output will have. You will have two real coefficient, or we can say basically two real coefficient of cosine format or basic cosine format. Okay. So some of the property, as we have discussed in the previous, in case of DFT, so many property, 10 basically 10 property we have discussed. So in case of DCT, there is not much properties are there. So we will discuss only two properties here. Okay. So first property is the DST is your real and orthogonal. Okay, whatever when you perform the DST, discrete Fourier transformation, so whatever result you get, the result will be in real format. Okay, and it will be an orthogonal. Okay, so what do you mean by orthogonal? What do you mean by orthogonal? The orthogonal means, if I suppose this is my f of x. Okay, now suppose I perform DFT over it. Okay, DFT over it. So what I get? I will get CUV. Now CUV will be in the form of matrix. Suppose I say this matrix is A. Okay, this matrix is A. Now this UV I represent in matrix A. Now what the property of this one? This property, first property of this one, the matrix A, first of all, it will be real and it will be orthogonal. Now if this matrix is orthogonal, then this property, this condition should be true. What is the condition? The condition is A into A transpose should be an identical matrix. Similarly, A inverse should be equal to A transpose. This is the orthogonal property. Here, this point you have to remember. क्या आपका देखना है? जब कभी भी आप इमेज को DFT करें, it will be DCT, discrete cosine transformation. So whenever I perform discrete cosine transformation, so whatever image I get, so I will represent in a matrix A format. Now this matrix, first of all, it should be real. All the elements, I can say all the elements of this matrix will be real. Second point, this matrix should be orthogonal in nature. If it is orthogonal, then this property should be true. This property should be true. That means whenever I multiply the matrix with the transpose of this matrix, then the resultant matrix should be identical matrix. Or I can say the inverse of that matrix. When I perform the inverse of this matrix, must be equal to transpose of this matrix. So this is the first property. Okay, it is real and orthogonal. Fine. Second property say the discrete cosine transformers has excellent energy compaction for high correlation data. So I already say, so one of the drawback of DFT kya tha? The energy compaction is very less. But in case of DCT, okay, discrete cosine transformer has excellent energy compaction. Okay, for highly correlated data. If data are highly correlated, that energy compaction is very much high. That is the reason. And this property should be true. This property should be true. That means whenever I multiply the matrix with the transpose of this matrix, then the resultant matrix should be identical matrix. Or I can say the inverse of that matrix. When I perform the inverse of this matrix, must be equal to transpose of this matrix. So this is the first property. Okay, it is real and orthogonal. Fine. Second property say the discrete cosine transformers has excellent energy compaction for high correlation data. So I already say, so one of the drawback of DFT kya tha? the energy compaction is very less. But in case of DCT, okay, discrete cosine transformer has excellent energy compaction. Okay, for highly correlated data. If data are highly correlated, that energy compaction is very much high. That is the reason. That is the reason we can perform image compression here. Okay, image को हम लोग image compression technique use कर सकते हैं, and that can be stored in less storage space. Fine. So second property, just remember, it has high energy compaction for highly correlated data. Third property is similar to separable property of DFT. As हम लोग DFT में पढ़े थे, क्या पढ़े थे? अगर two dimensional DFT है, so I can separate this in two different steps. One is your row wise DFT करते थे. Then I perform whatever image I get. Then I perform column wise DFT. Fine. Then I will get the final result. So similarly here, the separable property also valid. Okay, separable property is also valid for two-dimensional DCT. Okay. Now again, same technique. I will perform the entire DCT in two different steps. One in one-dimensional operation in row wise, and other is one-dimensional operation in column wise. Fine. So whatever the separable property we have discussed in case of DFT, that will be applicable for the DCT also. That means we will first perform DCT for one-dimensional row DCT. Then whatever result we will obtain, I will perform one-dimensional column-wise DCT. Then the result that will be equivalent to when we perform direct DCT. Okay. So the property, for the property related, you have to just remember these three properties. Okay. The first property, it is real and orthogonal. The second property is it is excellent energy compaction. Okay. And third property, it supports the separable property. Fine. So this is something about what you understand by discrete Fourier transformation. The first thing you have to understand with this one is why we are choosing this one. The reason is because in case of DFT, we are using the complex representation, due to which, okay, the pre-processing or computational is highly complicated. ठीक है, जो भी कंप्यूटेशनल कर रहे थे वो हाईली कॉम्प्लिकेटेड था, और आई कैन से दैट टाइम कॉम्प्लेक्सिटी इज मच हायर देयर. सेकंड रीजन था आपका the energy compaction in our DFT is not so efficient. Okay, so this is the main two reasons why we are gone for other transformations. Okay, fine. So then the reason we gone for other transformation. So in DHT, so when we are performing the transformation, okay, the actual frequency domain are represented in your two real coefficient. Now, how it is represented? In a two real coefficient of basis cosine function. Okay, then we have discussed the mathematical formula in one-dimensional and two-dimensional. So we are not interested in one-dimensional, so we will focus the mathematical formula. Or you have to remember the mathematical formula for the two-dimensional. Okay, two-dimensional, how to obtain the DCT and how to obtain the inverse of DCT. Okay, clear? Then we have discussed some of the comparison of images, okay, in terms of DFT and DCT. Then you just remember these properties, okay, these properties related to the DCT. So any questions regarding this? So there are 3 to 4 more transformation are there, but that is not mentioned in your syllabus. Okay, like KL transformation, slant transformation. Okay, there 2 more transformation is there, but as this is not mentioned in syllabus, so we will not cover for the time being. Okay, if the time will permit, then we will cover that transformation also. But that is also the transformation, KL transformation and slant transformation are also important. Okay, fine. Is it clear? So any doubt regarding this image transformation? Any doubt? So image transformation, so we have discussed two techniques. One is your discrete Fourier transformation and second is your discrete cosine transformation. Okay, okay, fine. If you are not having your doubt, so we will discuss the new next topic, that is your SVD. Okay, singular value decomposition. So there are two techniques basically we will use. Okay, so one is your SVD, second one is your PCA. Okay, principal component analysis. दो टेक्निक हम लोग बेसिकली यूज करते हैं फॉर इमेज रिप्रेजेंटेशन. Okay, better representation of image, or basically SVD is used for image compression, or basically image compression for the image compression purpose. Okay, so we will go for the technique called SVD, which is nothing but singular value decomposition, and one more technique is there, which is called your principal component analysis, PCA. Okay, these two topics are very important because not in the field of image processing, in every field. So whenever we require to decompose a matrix, okay, जब कभी भी आपको अगर किसी मैट्रिक्स को डिकम्पोज करना है, okay, into the different unitary matrix, okay, basically we decompose in a two different unitary matrix here by this technique, so that the representation and analyze will be much easier. Okay, that is the reason we go for the singular value decomposition. Fine. Now this is a mathematical tool, singular SVD. SVD is nothing but a mathematical tool or technique that has an application in many of your engineering problems. Okay, that is the reason I'm saying. So SVD जो आपका है, SVD stand for singular value decomposition. Okay. Now this singular value decomposition is nothing but a completely mathematical technique. Okay, a completely mathematical technique. Fine. And its applications are not limited to image processing. That means it is not only used in image processing purpose, it is used in many of the engineering problems. Okay, many of the problems are using this mathematical technique. Okay, the first, this is proposed in the year 1873 and 1874. Okay, and this is basically designed for the square metric. ठीक है, जो भी आपका ये जो फर्स्ट जब से प्रपोज किया था 1873 and 74 में ये टेक्निक हम लोगों ने प्रपोज किया था, लेकिन the limitation is you have to decompose only square matrix. It is not, this technique is not useful for the any other matrix which is not in square. But in 1930s में the Eckhart and Young, the two scientists who proposed this SVD algorithm for the rectangular matrix also. Okay, so what happens, as we know that every images are not represented in a square format. Yes or no? Generally, we will take for our convenience, we will take in square matrix representation. That will be n cross n. But it may be a case every images cannot be in square matrix format. So that is the reason this algorithm was extended. Okay, so whatever limitation is there, that means limitation is it is applicable till 1990s. This is applicable only for the square matrix representation. But in the year 1930s, now this SVD, the singular value decomposition, are now applicable for the rectangular matrix also. Okay. Now, what actually the this matrix definition say? So now the SVD say that the singular value decomposition of rectangular matrix. Say, suppose I am having a matrix A. Okay. Now suppose this is my matrix A. This is a matrix A. Now I can decompose this matrix. Decompose means I can divide this matrix into three different matrices. One is your matrices U, which is your singular matrix. Similarly, another is your matrix V. Then we take this is also a singular matrix. Then there is a diagonal matrix D. तो कहने का मतलब है जो आपको ओरिजिनल मैट्रिक्स होगा, whether it will be a square matrix n cross n, या फिर it is rectangular matrix. I can take either rectangular or either square and cross and okay. Now this matrix according to the SVD, if I performing SVD over here, now I will divide this matrix into three components. One is your U. Okay. Now U is basically your singular matrix because the singular matrix. Now size of it will be m cross n. But the size is m cross n, and it should be orthogonal. Remember, it should be orthogonal in nature. Okay, orthogonal या orthonormal बोलते हैं. So what is orthonormal? So can anyone explain what you understand by orthonormal matrix? So if I say use orthonormal matrix or orthogonal matrix, then what properties should be hold here for you? If it is an orthonormal matrix, just I explain क्या होगा? U into U transpose should be equal to what? Identity matrix, or U inverse should be equal to U transpose. This is the orthonormal property for any matrix. Just remember, what do you mean by orthonormal property? If U is orthonormal, then if I multiply U and U transpose, it will should give the identity matrix, or this will be false. क्या होगा? E inverse should be equal to U transpose. Okay, now this is the first decomposition. Now we will decompose this A into first matrix, which is U of size m cross n. Okay, now I'm considering for the rectangular matrix. Now this A is m cross n, or this size will be m cross n, and it's orthonormal. Similarly, V is also a orthonormal matrix. V is also orthonormal matrix of size n cross n. Okay, now I have to take transpose of V. Instead of taking the original matrix, I will take the transpose of V. And now D is your it will be n cross n matrix. It will be n cross n matrix. Okay, and it is a diagonal matrix. Okay, it is a diagonal matrix, or we can say diagonal matrix comprised of singular values of A. Diagonal matrix means now U will be something. It will having only diagonal like row 1, 0, 0, 0, now 0, row 2, 0, 0. Similarly, it will be row 8. Now this is D will be basically your diagonal matrix, and these values, row values, are be stored in your decreasing order. Now row values, now row 1 will be greater than equal to row 2, and row 2 is greater than equal to row 3. Similarly, is greater than equal to row 8. Okay, remember this property. Okay, what is D? D is nothing but your diagonal matrix. Okay, diagonal matrix means it will have only the diagonal element. Fine. And how this diagonal element are arranged? Now these diagonal elements are stored in a decreasing order. Okay, that means row of 1 value should be greater than row of 2. It should be greater than row of 3, like that. Row of n. Clear? This property is clear. So sometimes this is represented by sigma signal. Some book it will be represented as sigma signal. It will be decomposed as A is equal to U sigma Vt. Now what is the sigma? Sigma is a matrix. Okay, sigma is a matrix of diagonal matrix which is having the values in a decreasing order. So if you see the mathematical formula for this one, now this is the mathematical decomposition. Now you can see here. So what is the mathematical decomposition? Yes. Now A can be decomposed in 3 different matrices. Now first matrix, I can say it is U of in the form of row vector. Okay. Now what we are doing now, actually the rectangular matrix original matrix था आपका A, हम लोग उसको 3 component पर differentiate कर रहे हैं. Now this is your U can be, I can say this is my row vector. Now this is your diagonal matrix. Now V is your column vector, because we are taking transpose, no? So V is actually your row vector which is converted to column as we are taking transpose of it. I know that when I take a transpose of the row vector, it will be converted to the what? Column vector. Now this is the actual decomposition. So what we are doing now, I am decomposing this A actual matrix to 3 components. This is my U, this is my D, or sometime I represent as sigma, this is my V. The point is, these values, these sigma values or similar values